Hello everyone, thank you very much for joining me in that webinar. I am David Freno, Vice President of Marketing and Business Development at Silicon Mobility. Today we will see together how Silicon Mobility enables you to unleash SiC power devices capabilities in automotive traction inverter applications with smart control. But before jumping into our subject, let me introduce quickly Silicon Mobility. We are a fabless semiconductor and software company. Our mission is to deliver key technologies for building a sustainable future. It is why we design, develop, and sell performance controller, chips, and highly advanced software and algorithm for electrified vehicles. Application-wise, Silicon Mobility enables to improve the energy efficiency of electric vehicles. Our technologies offer better control of the key elements of the electrified powertrain system. Our solutions are used to control power electronic systems as inverters and electric motors, onboard chargers, and DC-DC converters. Our products are designed to support and facilitate the integration and adoption of advanced control methods into these systems. Currently, our solutions are used by many automotive OEMs and Tier 1s. Today, we will have an overview of one of our most advanced technology, the OLEA app inverter HE application for the inverter and electric motor control. HE stands for high efficiency. OLEA app HE is a part of a full stack solution which includes chips, software, and expertise. It is fully customizable for further differentiation. The software is flexible and modular and enables the development of inverter electric motor control platform. It includes breakthrough performance and efficiency, and we will explain today what is included exactly. It is ISO 26262 functional safety built and compliant to all automotive standards, and it can be used for very short time to market introduction. So, into some more details about this solution. Our chip, the OLEA T222 FPCU, is a powerful semiconductor. FPCU stands for Field Programmable Control Unit. It's an automotive qualified semiconductor designed to process critical information faster with 100% predictability and accuracy. OLEA FPCU is very versatile and can be used in any automotive real-time and safety critical applications. Part of that solution, we have software, so application software, and this is the OLEA app inverter HE that we talk about today. This is an off-the-shelf control software that runs on the OLEA FPCU and includes advanced algorithms dedicated to control efficiently and safely inverter and electric motors. Fully features, highly configurable and customizable to match any electrified powertrain system configuration, inverter technology, and motor technology. And third part of our solution is engineering services. Silicon Mobility's engineering experts support our customer all along their design, validation, and calibration process. Let's have a look on the OLEA T22 FPCU. It is built around an hybrid architecture that Silicon Mobility has invented. It combines a standard CPU. Here it's an ARM CPU, an ARM Cortex R5F running at 200 MHz, and specialized patent hardware. This first patent hardware is the AMEC. AMEC stands for Advanced Motor Event Control, and it includes programmable logic associated with mathematical accelerator, digital signal processing capabilities, and standard interface to actuators and sensors. It runs demanding control algorithm in real time, provide parallel and deterministic processing with known processing time. So clearly it removes software processing bottleneck that you could experience with conventional microcontroller, with a conventional multi-core microcontroller. FPCU also includes Silence, which is a patent automotive ISO 26262 functional safety technology that provides fast system fault detection, correction, and containment. So this architecture is pretty unique because the combination of software programmability with the CPU and hardware programmability with the AMEC makes a totally flexible platform, so software and hardware programmability, strongly real-time with guaranteed timing predictability, safe by design, but not only at semiconductor level, but also at system level, and open. We are software independent here because you can program it directly from model. About our software, OLEA App Inverter HE is a complete control application software that can be adapted to any electrified powertrain system. Around a fixed core module, here in green, which include regulation, position, modulation, and safety functions, several modules, so in orange on the right, come as customizable. For the sake of rapid prototyping, some complementary functions, so in blue on the left, are also provided, but they are not part of the app itself. Silicon Mobility also provides engineering services on top of the OLEA App Inverter HE to customize the orange module for our customer, so to adapt and to port the application to a target system. And we can also develop some optional specific software related to the internal connection to your VCU or to interface for system integration. Sorry. But what is unique to OLEA App Inverter HE is that in the modulation part, as we support the OPP modulation. OPP stands for Optimized Pulse Pattern. It is a modulation that enables to improve furthermore the efficiency of inverter and electric motor system and unleash SiC power devices benefits. So, for those not familiar with OPP, let's review what is OPP and how it differentiates from the conventional SVPWM scheme. Well, so back to the basics here. As you know, to increase the efficiency, we need to reduce the energy losses. There are two main sources, at the inverter level with the switching losses and at the electric motor level with the iron and copper losses. This is what we have today. The microcontroller generates a pulse width modulation, usually based on SVPWM, at a fixed or variable frequency to switch power devices and shape sinusoidal phase currents that will spin the electric motor. The higher the SVPWM frequency is, the better is the shape of the phase currents. The quality of the phase current is measured as a total harmonic distortion, so THD, percentage of THD. And if the higher it is, the more there are harmonics, and the more there are losses, noises, and vibrations in the electric motor. And this is where the trick is. The inverter and electric motor losses are linked. If you want to reduce the inverter losses, you increase the electric motor losses. And backward, if you want to reduce the motor losses, we increase the inverter losses. So there are nowhere around. Losses are bind. The only way to change this paradigm is to change one element of the system. And here, wide bandgap technology in power devices such as silicon carbide offers lower switching losses. So by using SiC devices in an inverter, immediately reduces the losses in that inverter in comparison to IGBT, for example. This allows an increase of the switching frequency and an improvement of the THG. But we can go further. To extract the maximum of efficiency, the control must be also changed. The conventional MCU needs to be replaced by a more powerful real-time controller, such as the OLEA T22 FPCU that I introduce later, sooner. The control software needs also to be changed with something that is more precise and flexible. And this is what optimized pulse pattern modulation is offering. Reduction of inverter and electric motor losses. So we have something that is better than SVPWM with SiC, with the OPP plus SiC. OPP is not a new control method scheme. It has been originally developed for industrial applications, and it is also used in motor control for train, for example. So here is a brief comparison between SVPWM and OPP. In SVPWM, pulse width modulated signal based on a fixed frequency are used to control the inverter switches to generate the desired multi-phase voltage to the electric motor. In OPP, modulation is entirely based on the motor electrical angle. Switches can be located at any angular position, and the number of switches can vary upon precise conditions. So I won't go into detail of that slide, but clearly the benefits of the OPP approach has multiple positive impact on the EV efficiency. So combining OPP running on the OLEA FPCU with 6 power transistor can lower the losses, so in the inverter and electric motor, lower the cooling demands, for example, downside the component needs, increase the power density of the overall system, and ultimately reduce the size and the weight of the element of the system, reduce the battery size while keeping the same range, and overall you reduce the weight of the vehicle and its cost. So this is clearly a big advantage. OPP is a part of the model-based driven predictive control world. It means that it needs a two-step design. In the first step, done offline, the OPP are generated for a defined set of operating points, so speed and torque, using an OPP generator solver. This tool uses motor and losses models to find the OPPs, so the best OPPs, suit for a target system. In the second step, the OPPs are used online in the embedded control software, depending on the operating set point. In the case of OLEA Inverter HE, Silicon goes even further by offering the possibility to apply the right modulation, so between SVPWM, DPWM, and OPP, upon the torque speed need. This is what we call the APC, Adaptive PWM Switching Mechanism. But let's first dig into the generator. So the OPP generator tools include 3 main functions. First function is a model of the system composed with the model of the inverter that you have here on the left, and the model of the motor and the model of the losses of the motor. Each of the models are configurable to match, obviously, the physical characteristic of the targeted system. The second function is a scoring function of the result. The scoring is established upon a cost function that is tailored upon the weight given by the user. It could be inverter losses, reduction, THD improvement, torque ripple minimization, or any composition of these constraints. And the last function is the digital solver, which seeks for the OPP within the multi-dimensional space, so on the bottom. So you have some kind of a recurring loop here that will seek into that multi-dimensional space to find the best OPP for each set point. Silicon Mobility has developed an OPP generator tool that we made available to our user, and they can define their optimization target and calculate the OPP pretty fast, pretty quickly. The tool is running on PC and accelerated by processing, accelerating its processing by using a GPU. We also offer a graphic user interface that enable the analysis and tuning of the OPP solution. Here you have on the right a screenshot of that GUI interface with a specific set point here, and where you can compare 2 different patterns depending on the switching frequency or equivalent switching frequency and the THD. Here we have a series of examples. So it's just a tiny example of 3 different modulations on the same operating set point. With the SiC inverter. You have on the left the reference SVPWM. It is switching at 18.7 kHz, and what we measure here is 6% of THD. If you apply a DPWM modulation on the same set point, you have an equivalent frequency switching, so equivalent because here you are not switching at a regular frequency, but you remove very tiny on and off on switches. You have an equivalent frequency switching of 16.6 kHz, so it is better somehow because you will reduce losses into the inverter, and you have also a better THD. But you can see that on the OPP you can go even further. So on the same set point, THD is achieving an equivalent frequency at 15 kHz, so less switching, so less losses, and a better THD. THD is improved at 3.7%. So we reduce somehow the quality, well, we reduce the losses into the electric motor by improving the quality of the control here. But the quality of the shape is not the only thing that is important. It could be also important to remove some specific harmonics in order to improve the behavior of the electric motor. So OPP can be combined with the well-known selective harmonic elimination algorithm to remove undesired frequency bands. In that example, we can see how OPP with CHE, so selective harmonic elimination algorithm, does better than SVPWM. And also, so SVPWM on the left here, you have a 10 kilohertz and THG of 10%. OPP, you can have the same frequency equivalence, but you clearly improve the THG. And if you apply selective harmonic elimination on it, so on the left here, you can see that you do not degrade the THG, but you achieve your goal by removing the targeted frequency. So these are some examples, and we can have many other criteria of evaluation. So let's go back to the software, so the execution of the software itself, the embedded software. And we find back here our OLEA Inverter HE control software. And we have seen now what is OPP and IPC stand for, so the red blocks. But how does our software behave in transient states? Because when we drive a vehicle, we are not staying always on a fixed operating point. And this is a problem that Silicon Mobility has solved when porting OPP on OLEA. Indeed, OPP are designed for stationary conditions. A train has typically that kind of behavior, because proportionally to the reduction of the number of switches, the OPP reduces also the ability of the system to be properly regulated. And by construction, transitions between patterns do not ensure stability. So what we did with OLEA Inverter HE, we have invented a new kind of or a derivation of the field-oriented control loop adapted to OPP. So it's a patented technology, so I cannot share today the exact implementation. But here you have some example on the right of graphs showing the transition between OPP. They are very smooth with a low ripple and very high response time. And this has been controlled. If you are comparing standard field-oriented control and SVPWM, so the graph on the left, compared to this closed loop, let's close loop that we have implemented with OPP, we clearly see that we have a torque ripple that is lower than the reference, and the torque response time is also lower. So clearly we have a better control, a smooth control here than a standard approach with better efficiency. OLEA App Inverter HE shares the same software platform as the OLEA App Inverter that we have presented last year during this same webinar. And it includes a state-of-the-art feature supporting a wide variety of electric motor and sensor. It is built with an ISO 26262 compliant functional safety features. It is designed with 4 different API for an easy and fast integration in a standard AutoSAR application software. So an element very important is fast prototyping. If you are interested to evaluate and use OLEA and our technology and the OPP, we enable fast prototyping, either with a generic control board that can be adapted to your inverter and electric motor systems. This is a picture on the left, provided by Silicon Mobility, or with inverter platforms available from partners. So we have 2 of them, and they are all SIG-based inverters. Let's see in a short video here. So this is our HV 2.1 inverter control board. This is a 3-phase inverter control board that can be adapted to any kind of inverter electric motor. You have all the connector for the motor interface and the vehicle interface. It's very, very flexible. We have also a SIG inverter platform that has been designed by Cisoid using Silicon Mobility technology. So you have, in fact, 2 control board, 2 digital board. One has the OLEA chip, and below you have the gate drivers of Cisoid connected to the power module of Cisoid. And this is a full kit that includes the cooling and as well the DC link. So it's a very handy if you like to design your own inverter. We have also a platform which is much more complete that has been designed with Voltspeed analog device. It's a 300 kilowatt SiC inverter platform. Here you find back our technology. So this is a pretty adaptable control board that's same, has all the connectors to connect to the electric motor and the vehicle interface. You have the 3 gate drivers board from ADI, and you can connect it directly to the electric motor and your battery. It includes, of course, the cooling, and this is ready to be used for closed loop evaluation. So it's up to 800 volts, 360 ampere of power. So to finish with OLEA Inverter HE, it includes debugging and calibration support, either with the ASAM standard solution, compliant with Vector Canapé or ITA-Synca, or for high performance with a very high data bandwidth. Will provide interface with Lauterbach probe and customized Lauterbach GUI for precise debugging and calibration phase. So everything is available upon your need. So this is the final slide of our webinar, and this is your takeaway. So what we have seen is that the OLEA FPCU and OLEA Inverter HE application software enables the development of efficient inverter and electric motor control. OLEA Inverter HE include the optimized pulse pattern modulation-based control and the OPP Generator Tool. OPP generation can be driven to reduce the inverter and electric motor losses, reduce NVH, and reduce torque ripple, among other key optimization criteria. And for fast prototyping of OLEA inverter, we provide platforms and inverter kits that are available right now. So I'm now ready to talk with you.